Today we'll be covering section 12.5 on conditional probability. I want to talk about the idea of independent and dependent events. I alluded to that in the earlier formulas when I put up those formulas in advance. Independent events are ones for which the result of one event does not affect the probability of the occurrence of the other. There are some simple examples that we'll go through, but I need to throw up the thing to contrast it with, which are dependent events. Dependent events are one for which the occurrence of one event affects the probability of the occurrence of the other. Now that you can see the contrast, I want to put some examples up and see if I can make it even clearer. Let's decide whether the following events are dependent or independent. Doing your assignments and passing your math class. Do you think doing your assignments might have some effect on the probability of you passing your math class? Yeah, I think most people would agree to that. So those are dependent events. One thing can affect the probability of the other thing. How about this? Running daily and winning the New York Marathon. Again, I think most people would agree that that might have an effect. That daily running might very well have an effect on how probable it is that that person will win the New York Marathon. So I'd say, again, those are dependent events. How about this? Winning the lottery and winning a spelling bee. It's really hard to imagine how winning a lottery could affect the probability of winning a spelling bee, or the probability of winning a spelling bee would have any effect on the probability of winning a lottery. So those two events are independent. Getting heads on a coin toss and rolling a 6 on the standard die. Flip a coin, does it matter what you get in terms of it changing the probability that you're going to roll a 6 on the standard die? No, I don't think so. So those are also independent events. This sort of gives you an example of what we mean by dependent and independent. You mainly need an intuitive idea of what they mean. How about this? Drawing an ace, then drawing a 2 from a deck of cards without replacement. Now think about this. If you draw an ace out, you don't replace it, and then you draw a 2, that does affect the probability, because since you didn't put that ace back in, you're only drawing from 51 cards the second time. There is a dependence there. Drawing that ace out and not putting it back in makes those two events dependent. If you put the ace back in before you drew again, then that would erase the dependence and they would be independent events. These are very important distinctions. You need basically an intuitive idea, but having an intuitive idea is extremely important. And this leads to something called the product rule for independent events. If two events, E and F, are independent, then the probability of E and F is the probability of E times the probability of F. That was one of the tools that I flashed up at the very beginning and said we would get to it later. Suppose you flip 2 coins. What is the probability that the first flip is heads and the second flip is tails? The coin flips are independent. What I get the first time I flip the coin has absolutely nothing to do with what I get the second time I flip the coin. So that means they're independent. So that tells me that the probability I get a head and then a tail is simply the probability I get a head times the probability I get a tail, because that's what the product rule for independent events says. Well, the probability I get a head is 1/2. The probability I get a tail is 1/2. So the probability I get a head followed by a tail is 1/4. A half times a half. That's the product rule for independent events. Just want to say that you could have worked this problem with a tree diagram. If you look at your first toss as being the first stage of a 2-stage experiment, the probability of getting a head is 1/2. And then once you've done a head, the probability of getting another head is 1/2, but the probability of getting a tail is also 1/2. So if you look at the branch that goes from heads to tails, you see it's 1/2 probability you get a head, and there's 1/2 probability you get a tail. And we learned earlier that the probability multiplying down a branch is the and probability. So the probability of getting a head and a tail, where the first is a head and the second's a tail, it would be 1/2 times 1/2, which is 1/4. So we did learn something in earlier sections that would allow you to get that same answer with a tree diagram. But treating it as just 2 independent events is much simpler. Now I want to talk about conditional events. That is the subject of section 12.5. And this is also where I said earlier we introduced some new notation. The conditional probability of event E occurring given that event F has occurred is the probability of the event E occurring taking into account that event F has already occurred. And that's what the adjective conditional means. Conditional probability means the probability conditioned on the fact that something else has already occurred. It's good probably to introduce this idea through an example. Let's let E be the event that the sum is 5 when we're rolling 2 dice. What is the probability of E? Well, that's just the probability we get a sum of 5, and we know how to do that. We draw our 2 by 2 table, and we count the sums that come to 5, which happen to be 4, and we get, by the basic probability principle, it's the number of ways of getting what you're looking for, which in this case is a sum of 5, divided by the number of ways you can get anything in the sample space, which we know there are 36 things, so it would be 4 over 36. If you want to reduce it to 1/9, you can. But what if I tell you that I've already peaked? I've done the die roll already, and I'm holding my hand so you can't see it, but I've peaked, and I'm telling you something about it. I'm not telling you what the sum is, but I'm going to tell you, well, I'm not telling you what it is, but it's odd. Does that matter? Does that change the probabilities because I gave you some new information? And the answer is, in general, yes, that will make a difference. So what I really want now is the probability the event E happens, which is getting a sum of 5, given that additional information, given that the sum is odd. That additional information is important because if I know the sum is odd, that changes the sample space because I don't have to consider any even sums anymore. So I can get rid of every sum that comes out even. 1 plus 1 is 2, that's even. 5 plus 3 is 8, that's even. 5 plus 5 is 10, that's even. 6 plus 6 is 12, that's even. So I can get rid of all of those. So that additional information is extremely useful. I can throw out the things that no longer contend because I know it's odd. The evens don't contend anymore. So the probability of E, given that the sum is odd, is just the number of ways that E can happen with that new condition, in this case that the sum is odd, divided by how the sample space changes given that new condition. So you're still doing a count of the event E, and you're still doing a count of the event S, but you're taking into consideration that something has happened and you have more information than you had to start with. That's what I mean when I say with condition. Well, once I crossed out all the even sums, there were 36, half of the sums were even. That knocks the sample space down to 18. There are only 18 odd sums. And then I look, none of these sums adding to 5 got knocked out because they were all odd, so there's still 4 of those. So the probability of the sum being 5, if I know that the sum was odd, is going to be 4/18. It would have been 4/36 had I not known that. So instead of the probability of the sum being 5 being 1/9, now the probability that the sum is 5 with that additional knowledge, that knowledge being that the sum was odd, now has doubled to 2/9. Yes, it does matter, or at least it can matter. You can see here the probability doubled. Knowing that information doubled the probability. So, to sum up, when we have a probability which includes an extra condition, and in this problem it was that the sum was odd, that probability is called a conditional probability, and we have a special notation for it. And if we go back to that previous example, the probability of E, I just wrote this sort of intuitively. The probability of E, comma, given that the sum is odd, we're going to modify that. I just wrote that out kind of intuitively. Suppose we call that condition F. In other words, the sum being odd is a new condition called F. So the sum being 5 was the event E. Now we're going to call the sum being odd the condition F. Then we'd write the conditional probability with this vertical line. The probability of E, and the vertical line is read as given that. So that's the probability of E given F. So that new notation, the vertical line is read given. So this is the probability of E given F. or given that F has occurred. Probability of E given F. That's conditional probability. This is important, so take a minute to just soak it in. The probability of E given F is the conditional probability of event E given that F has occurred. That F is the additional information that we now know that we didn't know before. The vertical line is read given or given that, depending on exactly how you want to phrase it. For our particular problem, this would be the probability that the sum is 5 given that the sum is odd. Think about that a minute, because you need to understand what the probability is saying or asking before you can get an answer. I want to give you a graphical way of thinking about this. You don't need this to solve any problem. You can do it with the formula, but it does make me feel better if I sort of give you a visual way of seeing why this formula works. So you've got an event E, you've got an event F, and you've got a possibility of overlap where E and F occur. That blended area where the circle E and the circle F overlap, or where the two events overlap, is E and F, or E intersect F. So the blended area is the intersection. The shading on the left circle E is blue, but it also includes the blended area. And the circle on the right, F, is the red area, and again, it includes the blended area as well. So you have the blended area is a part of both circles. The intersection is a part of both events, is another way of saying it. So the probability of E given that F occurred, if you know that F occurred, then you can get rid of the rest of E. If you know that F occurred, you don't have to worry about anything outside of F. However, part of E didn't get erased. The part of E that was outside of F went away, but the part of E that was inside of F stayed because it's in the blended area, the intersection. So you can see now that if you're counting the number of ways what you want happened, you want the probability of E, it's in the blended area. So when you count that, you're going to be counting from inside the blended area. And all that's left of the sample space is the entire circle F, so you're going to be counting everything in the circle F as being the sample space. It's like when we cut down the entire 36 possible sums to 18 because we knew what had already happened. In this case, part of circle E went away because we knew what had happened. It's just a visual way of seeing it. You don't have to know it this way in order to use the formulas. And conversely, if I want to know the probability of F given E, notice I'm given E. So that means that I know that E happened. So I can get rid of everything outside of E. So looking at the calculation, the only part of F that didn't go away is the part of F that was in the blended region. So that count goes in the numerator. And the only thing that didn't go away were the things inside of circle E. So now the sample space got reduced to the things in E, and you're left with that. So again, although you do not have to know this visualization, it does help you see where those formulas came from. The numerator gets reduced because part of one or the other circle went away, and the denominator gets reduced because of the same reason, part of one of the circles went away. So when you're doing the probability of E given F, you're dividing by the count in the F circle, and when you're doing the probability of F given E, you're dividing by the count in the E circle, and in the numerator, you're doing the blended area that overlap, the E union F. So again, don't have to know it, it's just a way of thinking about it if you're interested in seeing where these formulas came from. The main thing is that you know these formulas exist. Now, I did this as if we're dealing with equally likely sample spaces. If you are dealing with equally likely sample spaces, you can use the count. You're just counting things. If it's not equally likely, it's more complicated. The formula actually reduces to probabilities in both cases. So instead of saying the number of things in E intersect F and the number of things in E and F, I have to say probability both times. But most of the problems we work will be of the first type. So by and large, we can just think of it this way. And if I don't make any other point in this lecture, I want to say this and make this point. Oftentimes, if you understand how the given that condition restricts the sample space, the original sample space, you can solve this conditional probability problem without even formally using these formulas. They're there, sometimes you want them, but if you really understand how the given that condition restricts the original sample space, quite often you don't really even need these formulas. For example, if I told you that 2 cards are drawn without replacement from an ordinary deck of cards and asked you the probability that the second card is a heart given that the first card was a heart, I contend that you can solve these problems really without having memorized these formulas. They're asking me for the probability the second card is a heart given that the first was a heart. Well, if I know that the first was a heart, I'm given that the first card was a heart, then that reduces my sample space. If I know the first card was a heart, when I draw again, instead of having 52 cards in the deck, I'll only have 51 cards in the deck. And since the first card was a heart and there are 13 hearts in the deck, if the first card really was a heart, after I draw a heart out, I only have 12 left. So knowing that the first card was a heart, if I didn't put the card back and it says drawing without replacement, when I draw again, or just before I draw again, I'll be drawing from a 51 card deck that only has 12 hearts. So now the probability of that second card being a heart is simply 12 out of 51. And as I said, I didn't even refer to those formal formulas for conditional probability. I just figured it out based on common sense of what was going on in the problem. Knowing that the first card was a heart and that it wasn't replaced, reduced the sample space down to 51 cards, 12 of them being hearts. And that probability would be 12 out of 51. Simple if you know how to think about it. And if you want to reduce that to 4/17, you can. And as I said, I didn't even formally use those 2 formulas at the top of the page. How about this one? A container has 35 green marbles, 20 blue, and 4 red marbles. 2 marbles are randomly selected without replacement. If E is the event that a green marble is selected first and F is the event that the second marble is not green, compute the probability of F given E. I will say that when I see these problems where the events are given letter names, if they tell me what the actual events are, my inclination is to go ahead and replace the letters with an actual phrase representing the event. So if F is the event that the second is not green, I'll just write that out. And if E is the probability that the first was green, I will just write that out. It's up to you, but I think it's easier if you do it that way. Now, having done that, remember, we're given that the first draw resulted in a green marble, and we're doing it without replacement. So if there started off being 59 marbles, after the first draw, there are only 58 marbles, and the one that was drawn was a green. So instead of 35, there are 34 green. We want to calculate the probability that the second was not green, given that the first was green. You can see that I've already put the answer up there as being 24 over 58, and I think you can see that where that came from. The denominator is simply the count of how many marbles were left, and the numerator are the number of things that are not green, a number of marbles not green, and you can see that there are 20 blue and 4 red, and 20 plus 4 is 24. So there were 24 non-greens to choose from. So the probability is 24 over 58, non-greens over total marbles left. And it's 58 instead of 59 because you were drawing without replacement. If you want to reduce that, you can reduce it to 12/29, but WebAssign really doesn't care. How about this one? 2 dice a row. What is the probability that the sum of the dice is 6 given that the row was a double? Again, you want your sample space in a table 2 by 2, 6 possibilities for the first row, 6 possibilities for the second row. You're given that the row was a double. So we want the sum to be 6 with the additional information that we rolled a double. So the probability that the sum is 6 given that the row was a double. Well, if we know the row is a double, we know that's already occurred, we can get rid of everything but the doubles. Well, the doubles are 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So all of a sudden that 36 member sample space reduced down to 6 because we know that it was a double. So we'll be dividing by 6. Out of those remaining 6 choices, only one has a sum of 6, and that's 3, 3. 3 plus 3 is 6, so the probability is 1 out of 6, or 1/6. See how this works? If you can think it through, you don't really have to memorize the definitions. You just have to understand what the condition does to the sample space. How about this one? Mrs. Fraga's class has 109 students classified by year and gender. It's listed in the table below. She randomly chooses one student to collect homework. What's the probability of selecting a female given that she chooses randomly from only the sophomores? So the given that part is that she's only choosing from the sophomores. That means you can eliminate all the freshmen, all the juniors, all the seniors. So your sample space has reduced down to just the 21 sophomores. So now what's the probability of selecting a female? Well, look within the remaining choices, those 21 remaining choices, 5 of them are female out of the 21 sophomores. And notice again, I said it, but I'll actually write it. There are 21 sophomores, so the probability that the student was female, given that the person was a sophomore, is going to be the number of females over the remaining things in the sample space, which are just 21 sophomores. So your answer is 5/21. Very simple if you understand what you're trying to do. Now, conditional probability really is a useful concept in real-world situations. And one example is determining the efficacy of a drug test, maybe verifying some kind of genetic testing, evidence in legal cases. There are just tons of things. I've got a YouTube link here for you if you want to explore this on your own, but it really is a very real-life, useful thing to know how to do. Having said that, let's do an example. A test for a genetic disorder can detect the disorder with 92% accuracy, but the test will incorrectly report positive results for 3% of those without the disorder. Those are called false positives. If 10% of the population has the disorder, find the probability that someone testing positive actually has a disorder, and round that answer to 2 decimal places. When you read that, it just sounds overwhelming, but if you'll take the time to draw this out, do a tree diagram, and think about it in the right way, you'll see that this is not overwhelming. So I'm going to create an event called D, which means the person has a disorder, and then I'll use D prime to mean the person doesn't have the disorder, and I'll use the event P to indicate that the person tests positive, and I'll use P prime to indicate that the test is not positive, which in other words it means it's negative. And if I do that, I can think of the tree diagram as being, first of all, you either have people that have the disease or they don't. That's kind of the first stage in the experiment. And then if you have the disease, you can still either test positive or not. And if you don't have the disease, you can either test positive or not. So when you see a problem like this, if you'll just set it up as a 2-stage experiment with your tree diagram, I think you'll find that this is not unmanageable. Now let's go through this and figure out what these numbers are that are going to have to be transferred over to the tree diagram. First of all, I notice that 10% of the population has the disorder. So that means the branch on the ordinary probability for having the disease is 0.1. And if you want to calculate the probability that the person doesn't have the disease, that would be 1 minus 0.1. So 90% of the population does not have it, which is 0.9. You can see how I'm going with this. I'm going to transfer these numbers over to my tree diagram. So, moving along, it says that the test can detect the disorder with 92% accuracy. So in other words, if you have the disease, it will tell you that you do 92% of the time, 0.92. So if you have the disease, that means you went down the disease branch. You have the disease 92% of the time when the test says you do. That means that 1 minus 0.92, which is 0.08, 8% of the time the test is negative even though you have the disease. You hope to get that number smaller because you don't want to tell somebody they don't have the disease if they do. But in any case, in this particular situation, that happens 8% of the time. You also know that the test will incorrectly report positive results for 3% without the disorder. So if you go down that D prime branch, the test will say you have the disease 3% of the time. That's called a false positive. And you really want that number to be small. You don't want to tell somebody they have it when they don't. But in any case, in this case, you do have a 3% false positive. You don't have the disease, but the test says you do. And if 0.03 tests positive in this case, then 1 minus 0.03, which is 0.97, would test negative. In other words, the people who don't have the disease and test negative. And that completes the chart. From that chart, you should be able to get the answer to this question. We're trying to answer the question about the probability that someone testing positive actually has the disorder. In other words, the probability of D, have the disorder, given that they tested positive. So we're looking for the probability that the person has a disorder, that's the D, given that they've tested positive. Well, how do you do that? Since we're given that the test was positive, we can eliminate the P primes. In other words, we know now that the test was positive, so we can get rid of both branches that lead to the P prime, in other words, to the negative result. So now we're left only with the P branches. So our sample space has now been reduced to only the P branches. And remember, the formula says the probability of D given P is the probability of D and P divided by the probability of P. So if I want to calculate the probability of D and P, I have to multiply along those branches that remain to get the and. Multiplying 0.1 times 0.92, I get 0.092, and multiplying 0.9 times 0.03 gives me 0.027. So the convenience of reducing the sample space before I did the ands means I don't have to even calculate the other two branch ands because I'm not going to need them. So really, it's nice to eliminate the unnecessary branches before you do those multiplications. It saves you a little bit of time. So what is the probability of D and P? Well, that's just the product along the D and P branch, which is the 0.092. But what's the probability of P? That's the denominator probability. Well, there are two ways to get to P, and remember we did this earlier. If there are two ways to get to P, you've got to consider both. So you can get to P by going dP, that's with a probability of 0.092, but you can also get to P by going D prime followed by P, which is 0.027. So the probability of getting a positive result can happen in two ways. You have to add the two probabilities. So in the end, if you add 0.092 and 0.027, you end up with 0.119. We want to write this as a decimal rounded to two decimal places. So when you do that, you get about 0.7731, and rounding to two decimal places gives you about 0.77. So the two decimal places, the probability that someone testing positive actually has a disorder, given all these numerical results we have, is 0.77. So there's about a 77% chance that a person in this situation that tests positive actually has a disorder.